Up until this point in the quarter, we've focused on the structure of organic molecules. But starting today, we're going to transition from learning about their structure to their reactivity. As organic chemists, one of the things that we do is we take relatively simple molecules or building blocks and transform them into more and more complex molecules. And the way that we do this is through the creation of new chemical bonds, as well as the breaking of chemical bonds. It's very helpful when we think about the formation of new chemical bonds to think about the flow of electrons, generally from negative to positive. Before we learn about the nucleophilic substitution reaction today, I'd first like to introduce some key actors that will help us gain some context about the flow of electrons in this process. So the first actor will be the electrophile. And we can understand the electrophile a little bit better if we dissect the word into its two parts. The first part, electro, or electron, and the second part, phile, which comes from the Greek word philios, or love. So the electrophile loves electrons. And this inherent love of electrons is due to its electron deficiency, or in other words, some sort of positive charge or partial positive charge within the molecule. For the reaction that we're looking at today, our electrophile will be methyl iodide. And this partial positive charge is located on the carbon center. The partial positive charge comes from the electronegativity difference between the carbon and the iodide, which creates a dipole moment in the direction of an iodide that results in a partial positive charge. The second actor that I'd like to introduce is the nucleophile. We can dissect this word similar to how we dissected electrophile. We have nucleo, or nucleus, as well as love. So the nucleophile loves the nucleus. Which nucleus? It loves the nucleus of the electrophile, making the electrophile-nucleophile an important pair. The nucleophile is characterized by having an electron-rich atom, most often a heteroatom, which contains a lone pair and often a negative charge. In the reaction that we'll be looking at today, our nucleophile is the hydroxide anion. Now, finally, when we're talking about creating a bond with a carbon, sp3 hybridized carbon center, that carbon center is going to have 8 valence electrons, which have 4 bonds. If we would like to make a bond with this carbon center, we're also going to have to break a bond. And the way we do this is through a leaving group. A leaving group will allow us to break a bond from the carbon in order to facilitate the new bond being formed. Generally, we use halogens as leaving groups, and halogens are good leaving groups because they form a stable halide anion in solution. So within the reaction that we're looking at, we're going to have iodide as our leaving group here. Now, as I mentioned before, we want to think about the flow of electrons, and this flow of electrons is going to be from the nucleophile to the electrophile, and within the bond being broken to the iodide. And we can designate this flow of electrons using an arrow that's going to start at the lone pair of the nucleophile and attack the electrophilic center of the electrophile. At the same time, we can use a second arrow to designate the carbon iodide bond being broken, where we have the electrons of the carbon iodide bond then moving to the iodide. And this results in the formation of one molecule of methanol as well as the iodide anion. Now, in order for us to understand a little bit more about the mechanism of this reaction, we need to think about the kinetics and the thermodynamics as the reaction proceeds. And to do this, we can look at a reaction coordinate diagram. In the reaction coordinate diagram, we have energy on the y-axis, and we can think about the energy as the reaction proceeds. On the left here, we have the starting material, and on the right side, we have the products. Notice in the product, the energy is lower than the starting material, which means that we have an exothermic reaction. We can also look at the highest energy point in the reaction, which we call the transition state. In the transition state, we have 5 different things actually coordinated or making bonds with this carbon simultaneously. We have a partial bond between the hydroxide, a partial bond being formed with the carbon, as well as a partial bond with the iodide, which shows that the new bond being formed is happening at the same time as the bond being broken, so it's a concerted process. This concerted process is where the nucleophilic substitution reaction gets its name. The 2 in the reaction mechanism stands for a bimolecular rate law in the transition state, which is a collision of 2 molecules. The last concept that I'd like to introduce for this reaction is the inversion of stereochemistry. Let's say that we have a more complicated electrophile that has a chiral center. We can envision this electrophile going through a similar process where it's attacked by the hydroxide anion. And when we move to look at the transition state, we also have the new bond being formed at the same time as the bond being broken. Here it's important for us to notice that the bond being formed is on the backside of the bond being broken, and this results in an inversion of stereochemistry. While we have an R starting material, we're going to get an S product because of the inherent nature of this backside attack of the molecule. So this inversion of stereochemistry combined with the ability to form a new chemical bond is what gives the sn2 reaction utility for organic chemists. So at this point, I've provided on your worksheet some practice problems for you to go through. Please, on these practice sn2 reactions, try to identify all of the actors, so the nucleophile, the electrophile, and the leaving group, and also predict the product. You may work individually or in small groups on this exercise, and I'll come around the classroom to help facilitate the learning process.